Hello guys, now we start with some algorithm evaluation. We're going to start with the distance weighted nearest neighbors. It is an algorithm that's based on the k nearest neighbors, but it is a generalization actually of the k nearest neighbors. Suppose we have like two attributes in this input space. And let's suppose this attribute over here is like temperature, and this is like pressure or moisture, whatever. And then we've got some elements that belong to the positive class and some elements belonging to the negative class. The basic idea is we receive a new instance, and the traditional k nearest neighbors is going to consider the k closest elements to classify this one. For instance, if our k is equal to 4, I will say, okay, we have 4 elements that are green nearby this new instance, so the new instance is going to be classified as green. If my k nearest neighbor is like 8, I'll have 4 greens and 4 reds, so I will have like some uncertainty in classifying this new instance, which is like 50% green and 50% red. Of course, we can come up with some improvements, and the distance weighted nearest neighbors is a way of improving that. How it improves? It improves by considering Gaussian functions around this new instance. So if I have a Gaussian function around this central point, which is my new instance, I can consider a Gaussian with a spread that considers inside it like two reds and 1 green, so this point is going to be classified according to votes as red. If I increase even more my Gaussian function, in this case I will classify as green because I have a majority of votes for the green class. And if I increase even more in this illustration, of course, I'll have 3 reds and 3 greens, so I will be uncertain about classifying as either green or red. So the point is, I can change the width, the spread, or the standard deviation, if you prefer, of my Gaussian function to enclose more or less points around my new instance. You can imagine this like, okay, we have like a space, and when I arrive in that space, I can be classified according to my neighbors, according to my vicinity. If I'm closer to a certain kind of person, a certain kind of let's say could be in terms of whatever you guys imagine, I could be represented in terms of my neighbors. That's of course if my space makes sense. If my space doesn't make like any sense, this vicinity is not relevant. It's not going to bring any sort of information. Okay, but of course I'm going to consider it brings information. In this scenario, I'm going to implement our distance weighted nearest neighbors. I'm going to write here our first example. I'm just creating here a directory, and inside the directory, I'm going to develop our DWNN, distance weighted nearest neighbors. Okay, getting inside, I will depend on some functions to provide my result. First of all, I will have some weight function. The weight function is something quite simple. I will provide some distances over here and some spread of my Gaussian function, which is this sigma term over here, as you guys can see. The distance is the difference from my query point, which is my new instance, to an instance I have in my data, in my knowledge base, or in my training base, if you guys prefer to call like that. And this is the Euclidean distance. This is basically the Euclidean distance, okay, or the Euclidean norm to the square, as you guys may notice. So I receive distance, and what I'm going to compute here is the exponential of minus the distance, the Euclidean distance I'm going to use in my case, power to 2, divided by 2 times sigma to the square. And return this as the weight. What is the effect of this? Let's assess it. Let's take a look on this function. Yeah, it would be interesting. Maybe I could start like this. Just load my code. This is the way I'm going to load my code in R. And R is the language I'm going to use with you guys especially because it's a simple language, like quite easy to start with, quite similar to MATLAB. And it's got like a bunch of packages we can use. Yeah, it's quite interesting. This is the way I load my code, and I will provide to the weight function some distances. Let's say I will provide a vector. This is the way I create a vector. With the C parenthesis, I will send a distance equals to 0, a distance equals to 1, to 5, and a distance equals to 100. And my sigma is going to be, for instance, it could be 50. Let's start with 50. If I start with 50, the closest, which is the distance equals to 0, is always going to provide a relevance, a weight equals to 1. This guy is close enough, but it's not 0. So it's going to give a smaller importance, but quite close to 1, as you guys might notice. For 5, it's going to give this, and of course, for a very far point, it's going to be quite small. If I come up with a point which is really far, what's going to happen is that that particular point will have a weight or a relevance equals to 0 in my classification. So this weight function defines the relevance a point has in the space according to its distance to my new instance to be classified. If I reduce my sigma, take a look what happens. I will reduce even more the relevance for that point whose distance from my new instance is 100. So it's going to reduce. Take a look over here and here. The same is going to happen with the point that has a distance of 5 to my new instance. The same is going to happen with this point that has a distance equal to 1, and the one whose distance is 0, it doesn't matter. It's not going to change. If I reduce even more my sigma, take a look. No relevance for that point that's really far. Almost no relevance for this point, which is really far too. And for this point that has a distance equals to 5, it's got like 0.6 as relevance. This point whose distance is 1 is 0.98, and this point it's still like 1, okay? Let's say now my sigma is quite small. That means my Gaussian function is enclosing inside my space. If it's enclosing, every point that's a little far is going to have a relevance equals to 0, but the point that has no distance is going to be 1. What happens if this point is very close, like this, or maybe like this? It's going to have a high relevance, a high weight, because it's really close to my new instance. It's going to be really relevant. That's the same as you guys might notice. I could open GNU-plot and plot something like this. Plot the exponential, which is the same function as seen here, for a given distance to the square, and that's how we show to the square, multiplied by 2 times some sigma. Let's say my sigma is going to be 1 to the square. This is my Gaussian function in this scenario, assuming sigma equals 1 and my distance, my Euclidean distance, being represented by x. As you might notice over here, if I'm quite far, like 10 units of distance from the new instance, which is my central point, the weight is going to be 0. If I am very close to this new instance, my weight is going to be, take a look here, 1. And the farther I am from the central point or the new instance, the smaller is going to be my weight. That converges to 0, of course, and over here on this side too. If I come up with a different sigma, let's plot for sigma equals 1 and sigma equals 2. If sigma is greater, like sigma equals 2, I open up my Gaussian function to give weights to points that are even far than those points for the first one whose sigma was 1. And now sigma is 2. Of course, if instead of 2 I use like sigma equals 4, take a look what happens with my Gaussian function. It's going to open up. It's going to give relevance to points that have a distance equals to 10 from a new instance. So that changes the vicinity of my central point of my new instance, as you guys might notice. Okay? So having this weight function, what happens in my distance weighted nearest neighbors? What's going to happen is something like this. Someone is going to provide a knowledge, what we call knowledge base. Okay? The knowledge base is the same as the points I know and I have access to their classes. Instead of writing knowledge base, I'm going to write x for the input attributes and y for the classes I already know. And I will define over here some variable called query. My query variable is the one that I provide a new instance. Okay? It's the same as querying based on some data or knowledge I already have. So in this case, what I'm going to do is basically this. I will compute the distance that I have from every input instance to my query. And that's not difficult to make. Of course, I have I'm going to test something here. If my X is not a matrix, and if my Y is not a vector, I will not run. I will just return something like X must be a matrix, and Y must be a vector. Okay, just to make it simpler, just to ensure the data types are not going to bring like bad influences. What's like X? X is going to be something like this. I will have attribute 1, attribute 2, attribute 3, and so on, up to, let's say, attribute k. What's like my y? My y is going to be a vector like this. Okay, this belongs to class number 1, and this belongs to class number 2, and this belongs to class number 1 again, and so on. Okay? And so on. What's like my query? My query is going to be something like this. It's going to bring a bunch of attributes from 1 to k, and then I have to compute the distances. I have to verify what is the difference from this to this, from this to this, from this to this, and from this to this, to compute the difference I have, the distance I have from this query to this first example in my matrix X, or my input matrix X. The same is going to happen for the second example in comparison to the query, and the third example in comparison to the query. Of course, we have an easy way to perform that. We have a function called apply, and apply is going to work as a for loop. Apply on my matrix X along every row. 1 means row and 2 means column. Okay? So if it's it's going to call a function over here, passing the row as the argument. What I'm going to do with that row is basically a subtraction of that row in terms of my query. This is going to compute a vector subtraction. It's going to make this minus this, and this minus this, and this minus this, and this minus this. And after that, I will have a vector as an answer. And I can simply power to 2, sum up everything, and take the square root, and that's going to provide the Euclidean distance. You guys having time at home can just compute, just like in small parts, all those operations, and you guys are going to obtain the Euclidean distance over here. What I'm going to do with Euclidean distance? Assess the weights. Verify which are the weights for those distances. But of course, someone has to provide some sigma for me over here. And that's the sigma I will provide for the Gaussian function here. This will result in weights. This, of course, for this first example in my training instance, I will have some weight over here. Let's say the weight is 0. That means I will not take that into consideration. Let's say this is going to be, we'll have like a weight equals to 0.9, and this will have a weight almost equals to 0. So I will have one weight per example, per input example, per example I have in my input space, or in my knowledge base, as some people call. Okay? Observe what I can do with that. I can take those weights and multiply as in a dot product by y. What's going to happen here is basically this. Take a look. When I do y, I'm going to do it over here. I think it turns out to be easier probably. Like this. When I do y dot product with weights, this is going to result in 1 times 0 plus this 1 times this 0 plus this 2 times 0.9. This 2 times 0.9 plus 1 times 0.01. This will be the result, okay? And of course, this will give something like, let's see the result because I don't know it. It's going to be 1 times 0 plus 2 times 0.9, if I'm not wrong, yeah, plus 1 times 0.01, 1.81. And we normalize this result by dividing it by the sum of weights. What is the sum of weights in this case? Oh, it's 0 plus 0.9 plus 0.01. So the sum of weights, let's put like this, I think it's a nice way. The sum of weights is going to be 0 plus 0.9 plus 0.01, which turns out to be 0.91. When I normalize, I divide, of course, 1.81 by 0.91, and my result is roughly 2. As you might notice, it's going to be roughly 2. I have to comment here, otherwise it's going to fail. So in my case, over here, my result for this example, for this instance, will be 1.81 divided by 0.91, and that's the result. It's almost 2. So we are closer to 2, so our answer is going to be really close to 2. As you guys might notice, this distance-weighted nearest neighbors does not provide a discrete result, but actually it provides a continuous result. It's helpful to come up with regressions, with function regressions, okay? So in this case, my result will be exactly this. I will return this as my result. What can I do with this? I will come up with a linear test over here. Why a linear test? I'm going to try some different sigmas and show you guys the effect of my distance-weighted nearest neighbors algorithm. I will bind 2 columns. One column from -5 to 5 and the other from -5 to 5, 2. This is going to provide exactly a concatenation of columns from -5 to 5, from -5 to 5. I expect to give a number and make it right. So if someone gives me -5, I want to answer -5. If someone gives me 0, I want to answer 0. If someone gives me 3, I want to answer 3. If someone gives me like 2.5, I want to give a result equals to 2.5, which is in between 2 and 3. So I want to generalize that. That's going to be my data set. What's going to be X? My input space. What's my input space? It is the first dimension, just the first dimension, just, of course, these values from -5 to 5. In that scenario, I will organize those in a matrix with a single column. Why matrix? Because here I defined that that must be a matrix, okay? And in the case of Y, it's going to be a vector. So I'm going to extract the second column and make sure it is a vector, a numerical vector. I can also use here vector if you guys prefer. No problem. So now I will call my DWNN, passing my X, passing my Y, and passing some query as argument over here. And some sigma that someone will provide to myself over here. The query is going to be quite interesting. I'm going to build up the query with you guys. My query is going to be some number from -5 to 5. Actually, I'm going to divide this interval in 100 possibilities. What I'm going to do is I'm going to call my DWNN, passing my query along and collecting my result, my obtained result, my result in terms of the answer. And then I will come up over here with something quite interesting. This is going to save all results for me. Of course, it's going to be a matrix that I expect to bind in terms of rows. That's what row bind does. I'm going to bind my query and what I obtained for my query, the result of my query. Because now I can plot something like this. What I expected, what I had as input, and I expected as output, which is my data set. And I can also plot in terms of red points my result to verify how it looks like. Okay? This is going to be my linear test. So getting back over here, I will load up my DWNN source code and run my linear test. And in this linear test, I will define some sigma. Oh, let's start with 0.5, for example. take a look what happens. In black, we have, of course, our training set or knowledge base, as you might call it. So for 0 as input, I had 0 as output. For 2 as input, I had 2 as output, and so on. And using that particular sigma equals to 0.5, I could generalize a linear function in red, as you guys might notice over here. What happens if I change to 0.4? Let's see. Or to 0.3, let's see. Or to 0.2, let's see. Or to 0.1, let's see. Take a look. If my sigma is smaller, I will have a narrow Gaussian function. My Gaussian function is going to be going to spread out my space, but just in a narrow fashion. It's exactly like this. If my Gaussian function has a sigma equals to 0.1, it's going to open up like this. It's unfortunately GNU-plot does not plot up to 1 over here. It's a problem with GNU-plot, sorry guys, but that's how it works, no problem. What happens if I decide to increase my sigma to 5? Take a look. What's the comparison of a sigma equals to 5 and a sigma equals to 0.1? Guys, this goes up to here, but it's not plotted because GNU-plot has a problem in plotting this, a resolution problem, okay? Let me see if like this, no, it's not going to plot, it's a resolution problem, no problem. Okay, so if I open up more, let's see the result. What's going to happen here? If I select like 100, take a look. Or maybe 1,000, take a look. Or maybe 10,000, take a look. What's happening if my sigma is very large, like this? And what happens if my sigma is very small, like this? Or even smaller. Maybe my sigma could be like this. Take a look. Or maybe smaller. Or maybe even smaller. Observe that only the last point is red and black, and the first point is red and black. You know why? Because having a very small sigma, my Gaussian function is going to be very, very narrow around my new instance. And if I have it in my knowledge base, I will give importance equals to 1 for that particular black point, and I will be able of performing the regression for this and for this point. But what happens for the other points? I don't have any instance, any query instance, any new instance that matches perfectly those black points over here. None of those new instances match these black points. That means that any small perturbation I come here, I bring here in my input is not going to enclose this point in the vicinity. So I will not take it into consideration. Let's assess it. Let's understand what's happening here. Take a look at this. I'm just going to comment this and comment this and define my sigma equals, I don't know, to 1. Doesn't matter. And run it. If I do this and I load my source, it's going to plot with sigma equals to 1. Now I'm going to define my sigma equals to a very small number. And I will run my DWNN passing my parameters. Which are my parameters? I have the parameters here, x and y, because I commented the function, so the scope keeps my x over here and my y over here. Now let's define my query as a number that I have in my knowledge base. For example, do I have -2 in my knowledge base? Yes, I do. Okay, and let's define sigma equals to this small number, quite small number. Take a look what happens. I will answer properly. But what happens if I bring quite small perturbation in my query? Maybe a perturbation that's greater. If I bring some perturbation that makes impossible my sigma function, my Gaussian function with this particular small sigma enclose none of the training points, which are black, inside the vicinity, what I will have is basically all the points I have in my training data set will have an Euclidean distance that's greater than the weights I can provide. So it's the same as doing something like this. I try to verify the weights for distances like 1, 2, 3, and 4, but my sigma is quite small. It's like this. All weights will be equal to 0 because I have no nearby neighbor in my training data. If I don't have like any near neighbor, remember, I will multiply this 0 by this number. This 0, because here is going to be a 0 because I have no relevance for that particular training instance. 0 times this and 0 times that. So I have zeros in my numerator and zeros being summed up in my denominator. And 0 over 0 turns out to be not a number. You know what is interesting here? Take a look. This is the memorization, the memory-based classifier. Because if I provide a perfect number that I have in my knowledge base, it's going to answer properly. It's going to memorize. So if I provide 0, -2, or -1, or +1, or 5, or -5, it's going to make it right every time. But what happens if I need generalization? If I bring some small perturbation, it's not going to answer properly. Even worse, if my sigma is even smaller, take a look, a very small sigma like this. If I provide 5, which is perfect, it happens in my training instance, it's going to make right, it's going to answer properly because it's memorizing my data. What happens if I bring a quite small perturbation here? Not a number. It's not generalizing. That's the same as coming back over here and plotting to you guys this linear approximation. Again, this linear approximation for a sigma, a very small sigma, like 10 to -7. Oh, sorry. Sigma equals to 10 to -7, isn't it? Or it's not? Let me see. Oh, sorry, I'm just setting sigma equals 1 here. Sorry, guys. Just removing it and loading my code again. Yeah. Take a look. It is providing the correct answer for the first and for the last. Why? Because this sequence I'm creating here is properly starting -5 and going up to 5 and considering 100 points inside that particular range. 100 points makes only the first and the last to happen. The others are just very close, but they are not actually -4 or -3 or -2 or -1 or 0. Okay? You know what's interesting? What happens if my sigma is infinite? If it's infinite, I'm going to provide the average. The average over all my training instances. Why the average? Why the hell the average? Because if I give let's go back here. If I set sigma equals to infinity, I'm just considering R defines infinity. Of course, infinity is indefinite, we know it, but it's going to define as the greatest as possible value, okay? And it's going to pass that as my sigma. And when it comes down to my dWNN function over here, I will measure the Euclidean distances as before. And when I measure the weights, what's going to happen is, it doesn't matter the distance. If sigma is infinite, my Gaussian function is going to open up along the infinite. It's going to be like this. If I had here a very, very large sigma value, take a look what happens. Ooh, it's even possible I should reduce it. It's very hard to know what's happening. Let's reduce it. Oh yeah, now it's plotting. It's plotting here. But actually I have to select this. Oh yeah, like this, I suppose. Let's see. Yeah, I think you guys can see like some green function on top. Let's see if you can notice. Yeah, the green function is here. You guys can see that now my Gaussian function opens up. It goes like to the right and to the left. Of course, if my sigma is infinite, it's going to open up to infinitely open. It opens up to the infinite. It doesn't matter the direction. If it goes to the right or to the left, it's going to open up like that, up to infinity. So, of course, if I give my weights, take a look. If my weight is given in terms of a distance, it doesn't matter the distance, and my sigma is equals to infinity, all the terms are going to have a weight equals to 1 because I have a single Gaussian function that opens up to the infinity because of the sigma. So every term will have the same weight. If they have the same weight, which is equals to 1, this is going to be 1 times 1, 2 times 1, and 1 times 1, all summed up, and all divided by 3, which is 1 plus 1 plus 1. That is the average. That turns out to be the result of the average. That's why if the average of this data set is 0, we are going to have a function tending to the average. And you know what's interesting? I'm just going to go back to the slides now and analyze our space. This is the space we're studying with, okay? If I select a bias with if I select an over restricted bias, how many functions I will have here? Let's say I will contain just a single function, which is going to be the function. It's going to be the average function. Why? Because this is the space when I have a single Gaussian function. What is the case? Which is the case when I have a single Gaussian function in terms of my input space, which is represented in terms of this axis over here. That Gaussian function is, of course, the Gaussian function provided by sigma equals infinity, because this is going to open like going to the infinity on the right side and left side and never touch this axis. So it's going to open up, and every training sample I have is going to have a weight equals to 1. So I take the average. Just analyze this. If my sigma is very, very large, I am selecting a very restricted space of admissible functions, aka a width and bias, and I will contain a single function. If I start decreasing slowly by sigma, I will be increasing the space of admissible functions. Of course, if my sigma is very, very, very small, I will tend to contain the whole universe of functions. Actually, we can prove, actually I proved that in a paper, that if my sigma goes down to the limit of being equals to 0, I will be able of representing the whole space of admissible functions f all, the whole universe. The whole universe, I'll be able. Why? Just imagine. Why how can I see that? Of course, if I reduce my sigma very, very much, every point, every query point I have in terms of this input axis, if I bring a small perturbation, I will have a different Gaussian function. If I bring a small perturbation, another Gaussian function. If I bring another perturbation, another Gaussian function. How many functions I have here? Take a look. Many more. How many functions I have here? Just one. That's why my bias is restricted. So you guys can see the distance-weighted nearest neighbors as a very nice example to understand the algorithm bias by changing a quite simple argument, a quite simple parameter, which is sigma, which is this sigma over here. What I want you guys to test now is to come up with a different scenario. And that's what I'm going to do with you guys. I'm going to model a sinusoidal function. And that's, of course, more complex. If it is more complex, the question is, if something is more complex, do I need less functions in my bias, or do I need more functions in my bias? I need more. But not that many as in this picture, because if I go to the universe of all functions in the universe, I will, of course, represent a memory-based classification. That's an issue. Okay, just consider a different scenario. In this scenario, I will define a sinusoidal function 2 times pi times a sequence from 0 to 9, and let's start here, whose length is going to be like 1025. This is going to be my sinusoidal function, or my time series, so to speak. Okay, that's my time series that I want to somehow predict. What I'm going to do is exactly this. I will take, actually not 1025, I will consider 1001. I will take from 1 to 1000 as first column, and the second column will start in the second observation and go up to the last. And I will bind those together. This is the same as I will provide some value in the position 1, expecting to find the second element. And when I provide the second element, I will expect to obtain the third. When I provide the third over here, I will expect to obtain the fourth as answer in my output space. So my x will be this, and my y will be that, okay? And this is going to be my data set, as you guys know. Okay, let's just do like this. Oh, sorry, like this, okay? So my x is going to be my data set given the first dimension. Of course, I need to organize this in a matrix with a single column, okay? And here I'll have my y as a vector defined in terms of my second column. And this will be a vector. What I'm going to do? I'm going to do something quite interesting. I'm going to consider part of this data set as training and part as test. So my point is, this is going to be the whole data set, okay? And here I'll have some X for training and some Y for training. And here I will have some X for testing and some Y for testing. Okay? And my idea is basically this. Take X from the first, for example, to, I don't know, 900, could be 900. And here, Y from 1 to 902. And my test will be the remaining examples from 901 to 1000 over here in X, and in Y from 901 to 1000 as well. And here I'm going to do something like this. I'm going to provide a query, which is going to be my query. It's going to be some element belonging from 1 to the number of rows I have in my test. So I will get from my test, okay, that particular element in the position I position, okay, that's going to be my query. I will apply that query in my DWNN, providing my training in terms of input space and in terms of expected results, okay? And my query goes here and my sigma goes here. And of course, my sigma has to be given as a parameter, okay? Over here, I will define, just to start, sigma equals like 5, doesn't matter, like the first sigma. And here I will have some answer, as you guys might know. And of course, I will save up all the results into a matrix. My results will be like this. Just bind along rows what I what I've given as query and what I've obtained as a result. And of course, at the end, I expect to plot my X test in conjunction with my Y test. This is going to be the expected result in black. And I will use some points in red to plot what I've obtained. Okay, guys? And that's going to be my sinusoidal test. Sin.test, and I will provide some sigma here, just a default sigma. Oh, there's a mistake over there. I know what's like. This is a vector, guys, so there's no comma here, just if it was a matrix. So loading up again and testing. Oof, there's another error. Let's see. Number of rows of my X test. Okay, let's see it. I think I need to ensure this should be a matrix. Yeah, that's what's happening here. I need this to be a matrix, and I need this to be a matrix as well. Sorry, guys, just my bad over here. Okay. Okay, that's okay. Let's see. Can I run it? It's going. Sorry, guys. No, that's not the result I wish to provide. Actually, I know what I want to provide. I just want to plot what I expect. That's better. I expect this Y, and here I have obtained. Let's save up just the Y, the obtained. Let's call here the yeah, it could be result over here, but we could save up in a vector instead of a matrix, saving up all those results in terms of Y, and this should be a vector instead of a matrix. I think this is going to be easier to show to you guys, like this. Okay, that's better. In black, what I expect, in red, what I've obtained. What happens if I increase sigma? Take a look, I tend to the average. What happens if I reduce sigma? 5, it brought like some perturbation. 3, 2, somehow perturbating. 1, oh yeah, that's interesting. Remember, if I reduce sigma over here, I'm going to have more functions in terms of this axis. That means my bias will contain more functions. That means my space of divisible functions is more complex. So if it's more complex, it can represent more complex functions, such as the sinusoidal in terms of the linear function. What happens if I use 0.5? Take a look, even better. And now 0.25. Take a look. Maybe 0.1. Very nice. Or maybe 0.05. Take a look. Wow, amazing. 0.01. Ooh, so good. Now I'm going to over-reduce my bias. Take a look what happens when I over-reduce it. Take a look. I'm going to reduce even more. I'm going to reduce even more, and even more, and even more. And you guys remember that I said that if I ask for a point that I have in my training sample, I'm going to classify it or perform the regression correctly. This is the case in here because I have those points in my training basis. My training base, my knowledge base. What happens if I bring up a quite small perturbation here in my query? This means what happens if instead of the perfect match with my knowledge base, I have like a quite small perturbation here. Let's say instead of having like a perfect 0, or maybe instead of here, I could bring the perturbation in my series. My series could have like some perturbation over here. Even better, quite small perturbation could be a mean equals 0 and a standard deviation quite small like this for all those 1001 elements. It's going to happen now if I have a small perturbation. Let's load and let's try again some sigma equals 0.5. Wow, good result. 0.25. Maybe I can increase the perturbation so you guys can see something happening here. Otherwise, the perturbation is so small that you guys cannot see it. So I'm going to use the standard deviation equals to 0.1. Let's see what happens with my chart. Yeah, even better. You guys see that I've got a very nice result. What happens if I decrease even more my sigma? Take a look. Or maybe more, 0.01. Or maybe even more, 0.01. Or maybe even more. Or maybe even more. Oh, I cannot classify. Why I can't classify? Because when I select a when I define a very small sigma, I will have a more than necessary complexity in my algorithm bias. That complexity makes my bias capable of memorizing my training instances, but never making right for unseen examples whose perturbation is even small, is very small perturbation. I'm going to reduce my sigma and we are going to notice even more. You are going to notice that at some point I will have the possibility of performing the regression correctly. Take a look. Not yet. Small, even greater, of course, this sigma, sorry. Oh, take a look here. I was capable of making this right, this point right, this other point, and this, yeah, that's all. Why? Because those points had some vicinity in terms of my knowledge base. Why? Because I'm selecting such a narrow Gaussian function that the other points, most points are just being memorized. So I've been considering such a complex space of divisible functions that inside this I am converging to some sort of memory-based classifier or regression function, in this case a regression function. You are going to see that classification and regression in practice are the same. They are the same. They are even implemented in the same ways. Okay. Now I'm going to increase a little more my sigma. Take a look. Oh, I could make right for some other points. Now I'm going to increase a little more. Oh, I can make right for more points, and so on. Of course, at some point, I can make right for all points that I need. So what you guys can notice here is that when I change sigma, I am adapting the bias. The bias to be more restricted, what means smaller or less complex, all synonyms, or when I decrease my sigma, I'm increasing my bias. I'm making it contain. I make it like more complex. It's going to contain more functions inside the bias. Again, a large sigma tends to infinity, quite small space of divisible functions containing in the limit a single function which is responsible for the average. Okay. On the opposite, when I decrease sigma, I'm considering a much more complex space of divisible functions which might eventually contain the memory-based classifier or the memory-based regression function. What's the problem here? I cannot reduce my sigma. What could I do over here? I could take advantage of this guy over here and perform some sigma selection strategy. Let's use this sinusoidal test to select sigma. And over here, I will define some range for our sigma. Okay? What I'm going to do is exactly this. I will have some obtained result in terms of y over here. I'm not going to plot this, not anymore. I will have some expected result. Oops, sorry, y-test. This is the expected result minus the obtained result. This is going to provide some divergence or error for me. I'm going to, of course, because here I have like a bunch of numbers, here a bunch of numbers. If I compute the difference, I have a vector. And the vector to the square, I will sum up and compute the Euclidean distance. So this will be an error. Or, if you guys prefer, a risk. Okay, guys, so that's a risk we had before. Yes. So what I'm going to do is this. Compute the risk. Okay. Compute the risk. Oh, by the way, I'm not going to do this over here. I'm going to do this outside. Actually, here, I'm going to do something like this. This y is going to be a vector. I'm going to save up all those results in a vector. I'm going to take this vector minus the expected vector and compute this overall risk. And this is going to be the risk for, of course, I'm going to bind around rows, and I will save up what is the sigma that provided, which is the sigma that provided the following risk. And I will plot sigma versus risk. Okay, and here I will vary my sigma values. My sigmas will be here. Oh, very nice. This will be the sigma variation. My sigma will start, for example, in 1 to -7 and go up to 1. And I will create like 100 sigmas in that interval. And I will test for all those sigmas and compute. Of course, wow, there is a mistake here, guys, sorry. I will compute here inside the risks, and at last I will plot sigma versus risks. Again, this is a plot in the X label. I will have sigma, and in the Y label I will have the risks, or risk simply. Let's try it. I'm not sure if this is going to work because many times I make mistakes because I'm doing things on the fly with you guys. So doing things on the fly is not easy, as you might notice. I expect, let's see what I'm going to obtain. I expect to have some convex function, some quasi-convex function, some quasi-convex risk function. Wow, guys, it's so good to be right. You have no idea. Take a look. The risk is greater, and then the risk reduces, and then the risk increases again for a range of sigma. I'm going to reduce my sigma even more. I'm going to consider sigma maybe to -10 here, okay? And maybe instead of 100 elements, maybe 50 or maybe 25, just to make it faster, okay? I'm not that, in the mood to wait like too long to get results. So let's use like less values for sigma. That's not so beautiful, guys. You know why? Because over here I'm getting like some not numbers, and not numbers don't work properly. That's not nice. Yeah, we're better with more numbers here, and maybe working just from 10 to -7 as we were working before, but maybe with more numbers, just the opposite. Or maybe I could, yeah, that's good. Yeah. I'm going to wait. Okay, I have to be in the mood to wait. Patience. Just let's see the final result. We're going to have a quasi-convex function. If you guys look for quasi-convex functions, you are going to see those functions have a convexity in a place, in a range for sigma, and then it becomes non-convex when sigma increases. Let's see the result. Waiting. And make it longer. Perfect. You guys see we have some sort of perturbation that goes up and then goes down. We have some region here in which we've got the smallest as possible error, and then it goes up again. Over here, actually, we cannot measure because not a numbers have been observed over here. If for every not a number that I observed, I added like some noise or some error, I will have a function like this that would start over here up and then go down like this and then go up again. So the best value, the best sigma is around this range. What's nice is that from this result we can select sigma. We can come up with the best as possible sigma for our problem. And defining that sigma, we are going to have the best as possible result for our problem. And in practice, we are defining what? The bias, the algorithm bias. We don't leave the bias to be over restricted, nor over relaxed. Guys, that's all for now. See you in the next video.